Yeah.
Yay. So Ben's going to talk about posterior distributions of transit times in Kepler.
Let me change this here. All right, can everyone hear me? Great. So thanks everyone for coming. And there's kind of a lot of things going on in this title here if you don't work on this exactly. Posterior distributions, transit times, Kepler data. So let's break it down one piece at a time. So if you maybe have missed the past 7 years of planetary astronomy, this is Kepler. It was launched 7 years ago this week. It's a telescope in space in Earth-trailing orbit that does one thing, and really only that one thing, but does it extremely well. It stared past tense now, at a region of sky about as big as your hand at arm's length, and looked at 200,000 stars, and every 30 minutes recorded their brightness. And it does this because occasionally these stars have planets, and occasionally these planets are aligned just right so that they pass in their orbit between the star and us. So if you observe the star as the planet passes along our line of sight, you see a decrement of flux as part of the stellar disk is blocked. And then eventually, as the planet continues on in its orbit, it finishes its pass in front of the star, and then the amount of flux you see goes back up. We call this a transit. And this is what it looks like in a really highly idealized case. You might imagine that it doesn't look like this in real life. And you're usually right. Sometimes they look beautiful. Here's a giant planet in front of a fairly small star, and you can really have some confidence that this is a transit here. But what about if the planet's fairly small? What if it's Earth-sized? Maybe it looks something like this. And so the black are the raw data. This is many transits folded on top of each other. And the blue is then this data binned, phase-folded data binned into small chunks. And so we believe there's a planet there, but this takes a whole bunch of transits to get there. And any one transit is a little harder to actually see it. Here's one transit of this planet. Anyone want to guess where the transit is? I'll take that as a no. I don't either. I looked it up. It's these two data points. This is out of transit. This is out of transit. This is in transit. And there's just noise everywhere else. And so it's really hard to characterize individual transits in a meaningful way for these small planets. And so maybe we don't care about individual transits, right? If you're going to bin them together, you're going to gain signal to noise anyway. So who cares about one transit? You should care about one transit. And this is because not all transits are created equal. If you have one planet and one star, as the planet goes around, you have the perfect two-body problem, and the transits occur exactly once per period. But if you have two planets, as they pass each other in their orbits, there's a gravitational interaction, energy and angular momentum are exchanged, and this causes then one of the planets to accelerate, one to decelerate. One transit occurs a little earlier the next time, one occurs a little later. You can see that right here with Kepler 9 from our very own Matt Holman. These are phase-folded to the period of the planet, the period, and you can see that some transits are early, some are late. And for the other planet in the system, you can see, maybe you can't see with this projector, but there's an anti-correlation. As one planet is arriving early, the black transit here is very late, and here it's very early. And take my word for it if you can't tell, this is a red transit. It's very late, and it's early on the other one. So there's often an anti-correlation here as the two planets exchange energy. So to really understand the dynamics of these systems, we need to actually measure the times of individual transits. Kepler natively gives us information about the radius of the planets, even a little worse than that, the ratio between the radius of the planet and its star, and the orbital period of the planet. Measuring transit times and dynamically modeling these systems tells us really about the rest of the orbits, the eccentricities of the planets, their mutual inclinations, the masses of them, or at least their mass ratios, and also non-transiting companions. If you only see one planet, but its times of arrival are varying, and you don't see any other transits, you know there's probably something else that's just not passing between you and the star. And so when people model transit times, they tend to look like this. This is kind of the state of the art. And I'm not knocking this. Like, people have done a lot of really great work, but there's ways we can improve. So on the x-axis is time, and each data point is a transit. And the point estimate is the estimate of the time of the transit relative to a perfectly linear ephemeris. And so transits that are higher are arriving a little later than you'd expect. Lower are arriving a little earlier than you'd expect. And so you can see there's some correlations. You can model this as some sort of maybe a sine function, something sinusoidal vaguely. Then you can integrate these systems and try to predict what this curve would look like. But there's a few issues here. These error bars are just error bars. There's a point and an uncertainty. And so you have to make some assumption about what that error bar is. And sure, maybe it's Gaussian. But if it is, then there's a lot of things that are 3, 4, 5 sigma away that are kind of hard to explain. You don't have this kind of 68% falling within 1 sigma of your expectations, like you'd expect for Gaussian errors. So maybe we should be concerned about just taking these at face value as Gaussian errors. Also, there's some data that are missing. There's a transit here, but it's not included. And these groups tend to throw out transits that don't fit their data, or there's a gap in the data, or anything else where there is information there, but it's maybe not quite as high signal to noise, not well explained by a pseudo-Gaussian distribution, and so they toss it. John? Oh, Ian. Yeah. Yeah.
So if you're plotting transit time variations, that I would think is a discretized quantity, and there are subsequent transits. There's no transit time variation at 0.5 orbital phase. Presumably you have some other quantity, which is maybe mean deviation from expected orbital position. Is that
So,
these models, or?
yeah, so there's some, like, T naught, like some time of a transit, and there's some nominal period that are used in here. And you can imagine if you get the period wrong, and you say the period is 10.1 days, it's actually 10.11, then you just have a slope upwards. And if you have the time wrong, everything is shifted up and down a little bit. If the time of transit 0 is earlier than you expect, everything shifts up.
It's not discretized because it depends on the ratio of periods of planets that are interacting, and that will cause continual variation, not discretized variation.
No, I mean, I guess my question is, what is the meaning of a measurement at time that does not correspond to transit in this model?
Say that again.
How can you define a transit time variation in between when the star is not transiting?
I see.
What is that?
Yeah.
What's predicting that?
And so it's not predicting that because we don't know what's going on between the transits. Yeah, Kepler gives us very specific information at one specific time. There is a transit going on or there's not. And so you can create some model of the planets going around that predicts them at every time. And that's useful if you also have radial velocity information. But if you're actually doing this analysis, as you do the n-body, you only just pick out these are the times of my transits, or this is what my light curve would look like, and compare to those.
That's an n-body simulation. Is backing up. Okay.
Yeah, exactly. Just to put what I just implied into words, the current best practices are good, but they're not perfect. We can do a little better. They assume Gaussian errors on the time of each transit. White noise is assumed in the light curve. Kepler has 2 modes of data, one with photometry every 30 minutes, one with photometry every 1 minute, and they throw out the 1-minute data. It's a lot of data, to be fair. They assume one transit shape. They don't marginalize over many different transit shapes, and they ignore ill-fitting transits. So here's an example of an ill-fitting transit. This is a really deep event. You can see it, but oh, shoot, it's not there. There's this big gap in the data. And so this one's not a trick. You could see this transit by eye if it were there. And you actually have really strong information. It's not here. and it's not here, but it's somewhere in this gap. And so you have some sort of uniform likelihood in between these, and that's really hard to capture in point estimate error bar. But if you're going to model this, this can actually be really constraining. If you have a model that says should be a transit here, you can really assign that a low weight. So we can do better. And so instead of just giving transit times, we can give posterior distributions of transit times. And so that's what I've been working on and what I'll tell you about today. And we do this using importance sampling. And has anyone ever used importance sampling in a couple? Okay, oh, kind of more than I expected. Great. We'll talk through, for those of you that haven't seen it, how it works. It's a Monte Carlo technique, not Markov chain, just MC, not MCMC. And so let's think about the canonical example for a Monte Carlo sampler. We want to estimate pi, or pi over 4, by putting down points and seeing what fraction of them fall inside an inscribed circle inside of a unit square. And so we put down a whole bunch of points, and we could add these up and see that something like pi over 4 of them fall inside the circle. But as you're doing this, if you have some idea of what the problem looks like already, you know these are the ones right near the center are really wasting your time. Those are going to be in the circle, and so if you already understand something about the area in there, you could just ignore those. So I could draw a different sample where I really bias my samples towards the edges. And so I decide, I flip a coin, and if I flip heads, it's a weighted coin. I draw near the edge of the sample. If I flip tails, just to make sure we're doing okay, I draw something from the inside. Totally fair. We can do that. But biasing our samples biases our results. This isn't going to add up to pi over 4 anymore. However, we know exactly what my bias looks like. I know how likely it is I draw from out here, how likely it is I draw from in here. So I can reweight my samples. If these are only 1/5 as likely, I give them all a weight 5 times larger. And then when I add up these samples, weighting them based off how likely it is that I would draw them, then we recover pi over 4. So that's the idea behind importance sampling. If you understand where you're drawing your distribution from and how likely it is you draw from your distribution, you can account for any discrepancy in your likelihood because of that. To put that into a visualization with a light curve, here's a transit. This is the same planet that we couldn't see earlier. The transit's probably right here, but we can take all of the time we wanted and just uniformly put down transit models all over time entirely, and try here, try over next to Ian, and most of those would just be a waste. We know the transit's right around here. So instead of that, we weight our important samples towards where we think the transit is.
Do you know that based on the rough estimate of the period?
Yeah, so we know vaguely what the periods are for all these planets, and the actual magnitude of the transit timing variations is much smaller than the orbital period. So we know roughly where the transit should occur. So I can put down one model, evaluate its likelihood, call that a day on that. But we know how likely this model is, and we know how likely it is that I would choose this model. We can do this many, many times. And now we have a whole population where we understand the likelihood of drawing each of these samples and their intrinsic likelihood of fitting the data. And combining that can build a posterior in the transit shape and the transit times. And so at the end of the day, that looks like this. Marginalized over all parameters except time. This is the distribution of times that I drew. And then this is the actual observed likelihood. Technically, it's a posterior, actually, because it includes a prior. But this is the likelihood of transit times in this distribution. And so then we can repeat this for every transit, for every planet. There's about 1 million of them. And build up a posterior that then people can use instead of just using the point estimates. in their n-body codes, actually inferring times of transit with their model, and then determining the likelihood directly that that fits the data. Jennifer. Jennifer, yeah.
How different are your posteriors from the estimates?
Yeah, it's a strong function of signal to noise. When you have a hot Jupiter, it's basically, we can measure times of those pretty well. As you move down to smaller and smaller planets, it becomes more and more non-Gaussian. The group at Penn State has looked into how well this works in a lot of cases, and the kind of Neptune-sized things can be well approximated by IT distribution. But as you move down to Earth-sized things, there's so much noise that it's so hard to see the transits by eye. There's lots of noise that gets captured as transit, and you have very multimodal distributions. And their posteriors are really the way to go. So as you move to transits that are the size of the noise, they really, really move away from Gaussianity. So the pros of important sampling are that it's embarrassingly parallel. I'm just drawing samples from a distribution that I understand and looking at data. There's no dependence on previous samples. So you can run this on, I use my laptop and then Odyssey and a computer in California, and they don't have to talk to each other. It's fast enough. We get the posteriors in the transit shape, and it's fairly simple to understand. You can just draw some circles in a square and have an example toy model. The cons are you need to know where to sample. So that's okay for this problem. It's not useful for every problem. And it's fast enough, but it's a pro and a con. Depends on how much computing power you have. And so I've just said haphazardly, oh, you just measured the likelihood of these transits. But that's a little bit of a tricky problem. I said earlier, the previous groups assume white noise only, so effectively they measure a chi-square. That's not always correct. Here are 4 transits of a giant object orbiting a red giant star. And so in the Kepler data, you actually see the red giant's P modes, oscillations. And that's this kind of blue model here that's explaining that. So this is very correlated noise. And then in the red are the eclipses, and the purple, pinkish is the sum of the two of them. And so you really need to model the correlations in that as well. And so luckily, we can do that because we have a lot of transits, but they're fairly rare. The star spends most of its time not being transited by a planet. And so for every star, we have lots of data of just what the star is doing that we can use to estimate what the noise properties are of the star and then incorporate that during the transit. And so for that, we use the Gaussian process, specifically an exponential squared kernel. The idea being that points are correlated with ones nearby, data points in time, and as you move further away in time, the correlation decreases. And so we fit for both the level of the white noise and the level of the correlation, both the magnitude and the time scale. And so if you imagine this being your covariance matrix, a white noise case, so white is perfectly uncorrelated, dark blue is very correlated. A white noise case would have values along the diagonal. Every point is covariant with itself, but not with anything else. And then we add in the correlated noise kernel, where we fit for how strong the correlation is and how long it lasts for. But in general, it has this shape. Points are correlated with ones nearby, and the correlation decays as e to the minus t squared as you move further away in time. And so just to summarize, we can infer the posterior distribution for every transit using our noise modeling and then importance sampling. And so at the end of the day, I showed you, well, at the beginning of the day, I showed you the points estimates. And so this is our version of that plot. Each column corresponds to a transit. And the white, and it's not the best color scheme, but the white corresponds to the probability of this transit as a function of time. So earlier, later, lighter colors, more likely. So then as you have some n-body code to measure times of transits, you can evaluate your likelihood along this curve directly. So it's transits in space, and it's really in posterior space. So we're doing this, we're done with this for all the single systems, working on the multis. Multis are a little trickier because sometimes you have two planets that transit at the same time, so you need to model them both. And the plan is that we'll put the posteriors online for anyone who wants to use them. And also the raw samples, if you want to reweight them in any way, or if you just want to use those directly. And the current challenge that I'm working on is star spots. And if anyone has any ideas, I'd love to talk to you later. The idea being that occasionally these planets, or these stars have spots, a little dark area on the surface of the star, and as the planet goes in front of it, it's blocking the bright part of the star, and then it blocks the dark part of the star. So there's a little less flux blocked, so you get this bump. And so this needs to be accounted for in your likelihood in some way. And so I'm still thinking about that. So thank you.
Okay, I think we have time for one quick question, perhaps, before jumping on the pizza.
I was wondering for a single system, for each transit, do you assume that the underlying transit light curve is the same shape for each?
Yeah. Yeah. So we assume there are no variations in the shape of the transits, which is generally true. There are a couple systems where we have seen either variations in depth or variations in duration from a change in the impact parameter. But it's only a couple systems that there's evidence for it. And so, in the first pass, we're willing to be wrong on those two to save from adding a couple extra hundred parameters.
So the only difference between one event and the next event is just the time, transit time. Basically the noise.
Yes.
All right, let's thank both our speakers. Thank you.
Thank you.
What do you use to put your posteriors online?
So we haven't actually put any online yet, but there's a website called Zenodo. Ian, Zenodo is the name of it? The data thing?
And it's all about pushing gray matter from conferences and stuff that's should be citable, but it's obviously not going to appear in a published paper in its own form. So they have a lot of space. Like you have a data set you want to put online,
Yeah.
they can set you up with an account.
Yeah, so they're totally willing to just put.
Or you don't even have to talk to them. You can set up your own account,
Yeah.
but they might give you more space.
Yeah, so they're just willing to have 80 gigabytes worth of samples just hosted by them.
That is awesome. Yeah, no, I also have very large multi-parameter spaces that at some point might be just good to put somewhere so people have their
Yeah.
work. So,
And it's too much. You can't put it on your own website.
I know.
All this. Yeah.
Very cool. As a speaker, I totally understand if you want to jump to the line. I should have told Casey that he's
Okay. I know the people in the back. I can talk to them.
awesome. Sorry, there wasn't more time for questions. We tried to be good friends with the high energy people.
Yeah. Figure out seeing around.
Okay, excellent. Is that yours?
It's ITC, yeah.
Do you have the box?
The box of, no.
The dongle box?